Welcome to the last session of 3711H. You'll be free after this. So we were talking about NP-complete problems, and we're going to continue doing that. We're going to see some more reductions today, and then I'm going to talk about what to do when a problem is an NP-complete problem. What can you do to solve it in the real-world cases? Okay. The last reduction we saw towards the end of the last session was a reduction from 3-sat to subset sum. And this was part of our proof of NP completeness for subset sum. Of course, the other part was showing that subset sum is in NP. And this was a bit of a weird reduction in the sense that we created really huge numbers. Okay, so let's go over this again. This is the problem of subset sum. I have an array of integers and I have some integer k. And the question is, can I choose a subset of my array such that the elements that I choose sum up to this desired value k? Okay, so the question is whether I can get a sum that is equal to this desired value. Now, I gave you a reduction from 3-sat, and the reduction was like this. I said that suppose I have a bunch of variables. So let's say I have v variables, and I also have c clauses. I'm going to create really large numbers, and I'm going to write these numbers in binary, of course. And every number is going to have several digits corresponding to each one of my variables and several digits corresponding to each one of my clauses. Now, I used 4, but we talked about this. You can use any number of digits. The main reason here is that I don't want to have any carrying from one part to the other part. And then I said that for each one of my variables, for each variable x, I create this binary number. This is a binary number where I have put a 1 in the place of x. I've put zeros for all the other variables. And then I go into my clauses and I look at those clauses. So if x satisfies clause 1, which it does, I would put a 1 in the C1 part. And then for C2, it doesn't satisfy C2. So if I set x to true, that would not satisfy C2. So I put 0 here. And then I said that I do the same thing for the negation of every variable. So basically for every variable, I'm creating 2 huge numbers, one for the variable itself and one for its negation. And the negation also just says which variables it's touching. So this is negation of x. So in the place of x, in the part of the number that belongs to x, I'm putting a 1. And then for y and z, I'm putting zeros. And then if I have not x, would I satisfy C1? No. So I would just put a 0 here. If I have not x, would I satisfy C2? Yes. So I would put a 1 here. And basically, the idea was that if I take a bunch of these numbers and sum them up, I want to satisfy all of my clauses. So I want to get 1s for every one of my clauses here. Okay. So I would like to have a 1 here and also here. But of course, I don't want to take a variable and also its negation. So I say that in the compartment of each variable, I also want to have a 1 in my sum. So I want to make sure that I have either taken x or I've taken not x. And if I take both of them, then I would have a 2 in this part, and that would not give me the sum that I want. Okay. Now, the only issue was that I might be able to satisfy some of my clauses in several different ways. For example, suppose that I have this clause, and let's say that I want to assign true to z and false to y. Okay. In this case, in my subset sum instance, that's like taking the number corresponding to negation of y and the number corresponding to z and adding them together, but they both have a 1 in the position for C2. So if I add them together, I will get a 2 here. I will get 0, 0, 1, 0, right? But I want to get a 1 here. So our solution for that was that for every clause, we also introduced some numbers, but these were negative numbers. And the idea was that I can subtract this clause. So if I've satisfied clause 1, let's say 2 times, I can subtract it. Basically, I can add this negative number, and that cancels out one of the satisfactions. And then we said that we add each one of these numbers twice to our set, so that if I have a clause that is satisfied 3 times, I can also get rid of the extra satisfactions. Okay, so this was a reduction. And again, you can check that the final subset sum instance is a yes instance, if and only if the original 3-set instance was a yes instance. So it has all the requirement of a reduction, and it's also a polynomial time reduction. But very importantly, the numbers that I'm creating here are huge numbers. This is a binary number that has, let's say, ON digits. It's 4 times V plus C bits. So this is not just subset sum over 32-bit integers. It's subset sum over any integer. But that's fine, because we're always talking about the size of the input, right? When we were analyzing the runtimes, when we were defining the problem classes P and NP, we were always talking about runtime as a function of the size of the input. And in this case, I can write my input, and its size is polynomial. The number of bits that I need is polynomial. So it's a polynomial time reduction, and it's fine. Okay. Now, I want to also show you another NP hardness result. So here's the thing. I know that subset sum is NP complete now because it's in NP and also NP hard. But in my subset sum instances, I also had negative numbers. What if I want to do subset sum with only positive numbers? Okay, so let's call this one positive subset sum. Is this also NP complete? Of course, positive subset sum is a special case of subset sum, right? I'm just saying that all the numbers that I'm giving you are going to be positive. And of course, the number k that I want as the sum is also going to be positive. So it's a special case of subset sum. So I definitely have this reduction, right? Because that's just a trivial reduction. When a problem is a special case of the other one, it's like if I have a solution for subset sum, I already have a solution for positive subset sum. And my reduction is just take any instance and use the same instance. But if I want to show that positive subset sum is also NP hard, I have to find a reduction in the other direction. Actually, it's easier to just find a reduction directly from 3-sat. So that's one of the reasons why I really like 3-sat. It's most of the time when you want to prove NP hardness, the easiest problem to work with is 3-sat. You can, of course, find any reduction from any other problem that you know is NP complete to positive subset sum, but let's do it from 3-sat. Okay. Now, how am I going to do this? I'm going to basically use the same reduction as before, but I just have to avoid negative numbers, right? So what was my problem? My problem here was that I could satisfy the same clause several times, and then the sum would not match up. And because the sum didn't match up, then I had to have a way of subtracting them. Okay, I'm going to just change this a little bit, and I'm going to write it in a different color because these are now 2 different reductions. I'm just lazy and I don't want to write them twice. Okay, so here's the thing. I'm saying that each clause should be satisfied exactly once. That's the intuition in this reduction. And then I could subtract some satisfactions of some clauses. What if instead I just say that every clause has to be satisfied 3 times, and then I can add satisfaction of clauses? So for positive subset sum, I'm going to have the same numbers as before, but I'm going to change my k. And I'm going to say that my k is going to have a 1 for each one of my variables. So if I have a 1 in the component of x, that means that I've either taken x or not x into my 3-sat solution. I'm going to have a 1 for the variable y, a 1 for the variable z, But then when it comes to this clause, instead of saying that it should be satisfied once, the intuition is that I say it should be satisfied 3 times. And here I also say it should be satisfied 3 times. Okay. And then I go here, and for every clause, in my previous reduction, I added these negative numbers twice. Now I add the positive numbers twice. So just make this positive and add it twice. So what's the intuition here? The intuition is that I take a clause C1, I want it to be satisfied at least once. But what I'm doing here is that I say I want it to be satisfied 3 times. But I also give the choice of satisfying it for free twice, because I'm adding this number twice, and this number is just satisfying C1, right? But I cannot use this number 3 times because I have only 2 copies of it. So one of the satisfactions has to come from one of the variables, one of the numbers corresponding to these variables or their negations. So that's how this reduction would work. Great. So this is now our picture. This is getting really long. I have to find a way to. Okay. So all of these problems are now NP-complete. And as you see, actually, if you look at this as a graph, there is a path from every one of them to every other one. You can check that there is only one strongly connected component here. So they all have the same level of difficulty. I've actually shown you reductions between any pair of them. Because if you want, for example, let's say a reduction from vertex cover to positive subset sum, you know how to reduce vertex cover to independent set, how to reduce that to clique, reduce that to CNF set, to 3-set, to subset sum, or to positive subset sum, right? So you can combine these reductions in any way that you like, and as long as there is a path, you can reduce the beginning of the path to the end. But now the thing that I actually promised to you at the end of the previous session, I'm now going to take positive subset sum, and I'm going to reduce this to knapsack. And actually, I'm going to reduce it to 0, 1 knapsack. Okay. Let's go to the end again. What is 0, 1 knapsack? It's basically a special definition of knapsack where you have 1 copy of each item. I don't remember when I was teaching knapsack, did I say that you have many copies of each item or just 1? I think I said 1. So if that's the case, then what you know as knapsack is already 0, 1 knapsack. So here's what I have in my input. I have a bunch of items, let's say n items. And I say that every item has a value and a weight, right? So the ith item has value vi and weight wi. Okay. And I also have a knapsack which has a limited capacity. Okay. So that's also given as input. So I have C in N, which is the capacity of my knapsack. Okay. Now, when we were using dynamic programming, I said that I want to take a bunch of items into my knapsack so that their total weight is less than the capacity of the knapsack and their total value is as high as possible, right? But in these sessions, we're talking about decision problems. So I want to turn this into a decision problem. So I also say that I give you some number K, right? And the question is basically, can you get a total value of K or more? Can you fit items into your knapsack that have a total value of at least K? And also, I'm assuming that all of these weights and values are also natural numbers. Okay, so the question, again, because this is a decision problem, is this: does there exist let's say some subset of the items, a subset S of items, such that, well, I want my items to fit. So I want to say that the sum over all items that are selected of their weight should be less than or equal to the capacity of my knapsack. And I want to say that they have the maximum possible value, but I've turned this into a decision problem. So I just want to say that their value is more than K. Okay, so the sum of I in S of VI is greater than or equal to K. You can also do equality. You can just ask, is there a subset such that the sum of values is exactly equal to K? This doesn't change the problem much because you can ask for K and K minus 1, right? Okay. So do we have this? Actually, let me go with the equality. This is my knapsack problem. We've already seen an algorithm for this, right? We saw a dynamic programming algorithm. What was the dynamic programming algorithm? It was very easy. I just said that I defined dp of I and let's call it C to be the maximum amount of money that I can make if I have the first I items and I have a knapsack of capacity C. Okay. Again, I don't know if it's better to do it with equality or inequality. Let me do it with inequality. Who cares? Hopefully both of them will work. Okay, so how would you calculate this? So dp of IC was supposed to be the maximum value of a subset of the first I items that fits in capacity C. Well, let me call it something else because C was my overall capacity. So let me call it D, capacity D. Okay. So basically, it was a very simple idea. It was that I'm either going to take the last item, item number I, or I'm not going to take it, right? So dp of ID was this. If I take item I have to look at dp of I minus 1, and then my capacity decreases by the weight of the item that I just took. But I'm also getting the value of the item that I took, right? If I don't take item I, then I just have to fill up my knapsack with the first I minus 1 items. And of course, I will take the maximum of these two. Okay. And then we have base cases where we run out of space or we run out of items, right? So the base cases are when we have 0 or when the capacity is negative, you cannot make it. So, and we saw the runtime here. The runtime was basically O n times C, where n is the number of items and C is the capacity of the knapsack, right? Because I'm calculating these dp values for every I from 0 to n and for every d from 0 to C. So I'm calculating ONC dp values, and for each one of them, I'm spending only constant time. Okay. But now I'm going to actually prove to you that this problem is NP hard. It's actually NP complete. It's definitely in NP because, again, if I give you a solution, you can check it in polynomial time. That part is easy. But I'm also going to show you a reduction, and it's going to be a very simple reduction that shows this problem is NP hard and therefore NP complete. And so if we have a polynomial time solution for this problem, we have proven that P is equal to NP, and we should get $1 million. Okay. What is the reduction? Our reduction is from positive subset sum. Okay. go to the next page actually. Reduction from positive subsets. So let's say that I give you an input to the positive subset sum problem. What does that input look like? I will have an array of integers. Let's call it A1, A2 to AM. And I have some number K. And the question is, can I get the sum of all of, can I get a subset of A such that the sum of all the elements in it becomes K? Now, subset is actually not the correct word. Multi-set, multi-subset. So I can have several copies of the same number, okay? I don't know what that's called. So I want to give a reduction from this to knapsack. Now, here's my reduction. I say that for each one of my items, for each one of the numbers in my subset sum problem, I create one item in my knapsack problem, okay? So for every I from 1 to M, create one item. Let's call this item I. And I'm going to give it the same value and weight. So I'm going to say the value of this item is equal to its weight is equal to the number that I had in my subset sum problem. Okay? And then I also say that my knapsack size is equal to K. I also set C equal to K. And K is also K, of course. That's why I didn't even introduce a new variable there. So basically, for each one of these numbers, I'm creating an item that has this number both as its value and as its weight, right? And I can do this because, remember, this is positive subset sum. I couldn't do this with normal subset sum because I could get negative values there. But this is positive subset sum, so all of these numbers are positive. So all of my weights and values are positive right now. Okay, and then I say, suppose that I have a knapsack of size K. So this is my knapsack, it has size K. And my question is, can I completely fill this knapsack? Can I fill it so that I get a total value of K? Okay, now because weights and values are the same thing, basically it means, can I find a subset of my items that sum up to K? Right, so this is a valid reduction. Again, you have to be much more formal than this in your final exam. But yeah, because you can't attach yourself and you cannot talk to us, you have to write everything, right? So, but this reduction basically shows that the problem of 0, 1 knapsack is also NP hard, and so also NP complete. So I have this picture now. We started from CNF SAT, we saw that all of these problems are NP complete. But does this make sense to you? If 0, 1 knapsack is NP complete, it means that if I have a polynomial time algorithm for 0, 1 knapsack, then I have a polynomial time algorithm for everything in NP, right? And we know that we don't know that. Like, we know that it's an open problem. No one knows if P is equal to NP. So I shouldn't be able to have a polynomial time algorithm for 0, 1 knapsack. But isn't this DP a polynomial time algorithm? Looks like a polynomial. Yes, that's the point. This is not polynomial time. Because when we talk about polynomial time, we're talking about a polynomial with respect to the size of the input. Now, when I give you this input, what is the actual size of this input? So how many bits do I need to encode this input? How many, let's say, elements do I need to put on my tape on my Turing machine? For every item, of course, I have to write its value and its weight, right? But then when I write this capacity C, I'm going to write it in binary, right? So it's going to take only log C bits to write C in binary. The same thing happens with K. It's only going to take log K bits to write this in binary. So what is my input size? My input size here is this. Well, first I have n, and in order to write n, I need log n bits to write it in binary. And then I have all of these items, and for each one of them, I have a value and a weight. Okay, so I have to give those values and weights. So this is the sum over every I of the log of wi plus the log of vi. Again, you cannot assume that these logs are constants, because I'm not telling you that these values always fit into 32-bit integers. That's not an assumption. These values can be any natural number. Okay. And then, of course, I'm writing C and K as part of my input as well. So I will get plus log C plus log K. So this is my input size, theta of this, depending on what alphabet you're using in your Turing machine. But if you want an algorithm that is polynomial time, it should be a polynomial in this input size. And C is exponential in this, right? N is not, because I have n bits here. This is the sum for every I from 1 to n, right? So my input size is actually more than n. So if I had an algorithm that was O(n), it would still be polynomial. But the C here, it can be exponentially larger than the size of my inputs. So this is a very important thing that you should never confuse. When we are doing complexity theory, we often use n to show the size of the input. When we're designing algorithms, a lot of the time we use n to show the number of vertices of a graph, or in this case, I'm using n to show the number of items. These are not the same thing, right? When you're analyzing your runtime, it's always based on the size of the input. So is your runtime polynomial in the size of your input? If I call this thing, let's say, I don't know what to call it. Okay, let's call it just size of the input. Is this bounded by some polynomial in the size of the input? Is this n times c less than or equal to some polynomial of I? And the answer is no. And I can easily create instances that show this is not the case. So just consider the instances where n is 1, and let's say these weights and values are also 1, but this c is a huge number, right? Then the size of your input would basically be O log c. But then your runtime is OC, which is like 2 to the power of the size of the input. So this is actually an exponential time algorithm. Okay. Great. Let me show you one more reduction, and then we will move on. Our favorite problem, 3-colorability. I want to go from 3-sat to 3-colorability. Okay. Let's do this. So again, just to remind you, what is 3-colorability? The input is going to be a graph, and it's an undirected graph. So I'm going to have a graph G, VE. And all you have to do is tell me whether it's possible to color the vertices of this graph with 3 colors so that no 2 neighboring vertices have the same color. So the question is this. Is there some function f mapping the vertices to colors, let's say red, green, and blue, such that for every edge, let's call it UV in my edge set, the color of U is not the same as the color of V? Does such a function exist? Now, 2-colorability is super easy. If I had only 2 colors instead of 3, asking whether a graph can be colored with 2 colors is the same as asking whether the graph is bipartite. And that's actually super easy. You can do it with BFS or DFS. Okay. But tree colorability is NP hard. Now, let's see why. So let's say that, again, I want to give a reduction from tree set to tree colorability. So I have a tree set formula. I have a tree set instance. Okay. Let's say my formula is something like this: X or Y or not Z, and not X or not Y or not Z. Okay. I want to create a graph such that that graph is tree colorable if and only if this formula can be satisfied. Now, when we were doing the reduction from tree set to, let's say, independent set, the idea was that I'm creating one vertex for each one of my variables, and the vertices that I take into my independent set are going to be the variables that are set to true. So this is a recurring idea in all of our reductions. It's like I change this instance to an instance of the other problem, and then I say there is a relationship between the solutions. If someone has a solution to that problem, I can change it back to a solution here. So somehow I have to create a graph such that if someone gives me a tree coloring of that graph, I can use that tree coloring to satisfy this formula. This is intuitively what I have to do. Okay. So here's the thing. Let's say that I create such a graph. And let's say that someone colors it. I can say that I take all the vertices that have a particular color, and I say that these correspond to the variables that are set to true. So let's say that I want to say all of my green vertices are the variables that are set to true. There's a problem with that. And the problem is that if you have a tree coloring, you can shift the colors, right? So as soon as you have a tree coloring of a graph, actually, if you use all the three colors, then you have 6 tree colorings of that graph, because you can just apply any permutation to the colors. Let's say you take all the green vertices, turn them red, turn all the reds into blue, and all the blues into green. That gives you a different coloring, right? But we don't have this kind of property in our SAT. I can't just randomly take some of the variables and change their truth assignments and hope that it would still satisfy. So I have to have a better way of reading which variables are set to true from my tree coloring. Now, the idea is that we're going to introduce a gadget, and this is the gadget I'm going to introduce. It's a triangle. Very inventive. Okay. And I'm going to give a name to each one of these vertices. I'm going to call one of them true. I'm going to call the other one false. And I'm going to call the other one dummy D. Okay. Now, this is a triangle in my graph. Because every vertex is connected to every other vertex, if I have a tree coloring of this graph, it should assign different colors to these 3 vertices. Okay. But now I can say if a vertex has the same color as the vertex true, that corresponds to setting the variable to true. Okay. And now this kind of shifting doesn't really affect me anymore. Okay. So this is my first gadget, but all we need here is that each one of them will have a different color. Now, just like the case of independent set, I'm going to create one vertex for every variable and also for its negation. So I'm going to create a vertex X. I'm going to create a vertex negation of X. Y, negation of Y. Z, negation of Z. Okay. Now, I want to enforce that only one of X and not X will be true. So only one of them should have the same color as the true vertex. Okay, the other one should not have the same color as the true vertex. How can I do this? Well, first I connect them together, so this ensures that they don't have the same color. Right? Then I connect both of them to dummy. Okay. So do this and this. Okay. Now, what happens right now if someone gives me a 3 coloring of this graph? Well, true, false, and dummy have to have 3 different colors. And if you look at each variable, it will not have the same color as its negation, but none of them will also have the color of dummy. So either X is going to have the same color as true and not X is going to have the same color as false, or vice versa. So I got to a point where I can actually encode this idea that I'm assigning true or false to each one of my variables in my 3 coloring. But this is not enough, of course. I have to now encode my clauses somehow. I have to encode this idea of X or Y or not Z. Actually, let me make it easier. Let's just make it X or Y or Z, because I don't want to take not of not. So I have X or Y or Z. How do I create a gadget for this class? What should I add to my graph so that it models this class? Well, here's a simple thing. Let's say I have 2 vertices in my graph. I have vertex A here and I have vertex B here. Now, we said that each one of these vertices is going to get a value, a color, which is either the color of true or the color of false. Okay. Now, I want to have a vertex that gets the color of A or B. Can I create a graph that ensures that's what's happening? So basically, I want to make sure that if I've assigned the color of true to either A or B, then I can assign the same color, the color of true, to this vertex. Okay. Here's what I can do, and I will always forget this, but it's a very easy thing. This is my only note for today. I just add 2 more vertices, and I do this. Okay. Now, remember that I have 3 colors, and right now I write my colors also as true, false, and dummy because they have different colors. So let's see what happens. First of all, if both A and B are assigned the false color, okay, then these 2 vertices cannot have the false color. But they're connected to each other, so they cannot have the same color either. So one of them is going to have the true color, and the other one is going to have the dummy color. So I either have this, TD, or I have this, DT. In any case, one of them is going to get the same color as vertex true, and the other one is going to get the same color as the dummy vertex. No matter which one, this one has to be colored F, right? So if both A and B are colored F, then this vertex is also forced to be colored F. Now, let's consider a different case. Let's consider a case where one of A and B is colored true and the other one is false, okay? Now, everything here is symmetric, so I'm not going to do the opposite again. So if this is colored true and this is colored false, what color can I assign to this vertex? I cannot assign false, right? But I can assign either dummy or true, right? What color can I assign to this vertex? I cannot assign true, so I can assign either dummy or false, okay? But remember, my goal is to assign true here. So what do I do? And these 2 vertices cannot have the same color. Well, I would just assign false to this one, and I would assign dummy to this one. And that ensures that I can assign true to this vertex. Okay, so the thing that I want to prove here is that I can assign true to A or B if and only if I have assigned true to either A or B. Okay, so if both A and B were false, I was forced to make this one false as well. Now I'm seeing the case where one of them was true, and I showed you that it's possible that I color it so that this vertex also becomes true. Okay. Now let's consider a case where both of them are true. So if they're both true, great. I can just color one of these false, one of them dummy, and then I can color this one true. Okay. So basically, the nice thing about this gadget is that it helps us compute OR in some sense using tree coloring. It makes it so that I can assign true to this vertex if and only if I have already assigned true to at least one of these two vertices. Okay. So what is my clause here? My clause is X or Y or Z. So, but here I know how to do one OR. I want to do two ORs. I want to have X or Y or Z. Well, I can just take this one and I can include it in another gadget that looks exactly like this, right? So I'm going to take X and Y. Okay, here's the thing. It's really hard to draw this graph. So I'm going to draw the same vertex again, but they're the same vertex, okay? So I have X here, and this X is the same as this X. It's just one vertex. It's hard to draw it. That's why I'm doing two copies. And I have Y here, and then I have this gadget from before. And I know that this vertex basically corresponds to X or Y. But I want X or Y or Z. So I'm going to create the same gadget again with Z. So I put Z here. I put two vertices here. I do this. Okay. So this one is now X or Y. This one is X or Y or Z. Okay. Just applying the same idea here twice shows that the only case that I can assign true to this vertex, the color true to this vertex, is if I have assigned the color true to at least one of these three vertices, X or Y or Z. Okay. And again, this X is the same as this X. They're the same vertex. I just can't draw this inside this. It's hard. Okay. Great. So this is what I'm going to create for every one of my clauses. Every one of the clauses in tree set, I'm going to have this for it. So the next one was not X or not Y or not Z. Very easy. I'm just going to create the same kind of gadget. It's just that now this is not the X vertex. This is the not X vertex. Oops. And this is negation of Y, and this one is negation of Z. Okay. But this is still not done, because what I've proven so far is that I can assign true to this vertex if and only if I have assigned true to one of the three components, X or Y or Z. Okay. And here it's also the same. It's like I have not X or not Y or not Z. And I can assign true to this vertex if and only if I have assigned true to this one, or this one. Okay. But of course, I want to also force the coloring to assign true to this vertex, because I want to force the coloring to satisfy this class, X or Y or Z. And I want to force it to assign true to this one as well. So how do I force this one to be true? Well, I can just connect it to both dummy and false, right? If it's connected to both dummy and false, the only color I can assign to it is true. And I do the same thing for this one as well. You see, this shape looks awful, but so it's dummy and false. Oh, it went over that one. Okay. This is my graph now. Now I claim that this graph is tree colorable if and only if the original tree set instance is satisfiable. Okay. Now that's pretty easy to prove. So first, let's say that my instance is satisfiable. If my instance is satisfiable, there is a way of assigning true or false to these variables so that every one of these clauses is satisfied. So I take all the variables. So I first assign colors to true, dummy, and false. I don't care what permutation of colors. And then I take all the variables that were set to true in my assignment, and I set them to the same color as true here. And I set their negation to the same color as false. And then here, I will do the coloring that I showed you here, like tons of casework. But that would ensure that all of these vertices will get the color true, which is fine because they're only connected to dummy and false. Okay. That part is fine. Now, the other side. Let's say that this graph has a tree coloring. Okay. It does actually have a tree coloring. So here's a tree coloring. Let me use green for true. And let me use red for false. And I use just nothing for dummy. Okay. So what are the variables that I want to set to true? Let's say I want to set y and not z and x to true. And now, actually, let me use blue for dummy. Now let's look at this vertex here. It has a blue neighbor and it also has a green neighbor. So it has to be red. So I have to make this one red. This one also has a blue and green neighbor, so this one has to be red as well. This one has to be red as well. Okay. Now remember that this vertex was the same as this one. So it's actually already green. Y is also already green. Z is red. Not X is red. Not Y is red. And Z is green. Not Z is green. Okay. I have to still assign colors to the rest of them. So let's see. I want to assign green to this one and green to this one because they already have red and blue as their neighbors. And now this one has to be blue. This one has to be red. What else? So I have red here. I can actually have dummy here and here. And I can have green here. And here I can have dummy and green. And then I can make this one red. And then this one can be blue. This one can be red. Okay, this is a tree coloring. Okay, so let's say someone has given you a tree coloring of this graph. How can you find an assignment to the variables? You just take all the variables that are the same color as true, and you say, I set them to true. And I set all the other variables to false. Now, first of all, this is a valid assignment in the sense that every variable is going to get either true or false, and its negation is going to really get the negated value. That's because they were all connected to dummy here. And secondly, it's going to satisfy all of my tree set clauses because the vertex corresponding to each clause is colored true. It's colored green in this case. And again, we go back to the correctness of this gadget and we saw that this gadget works. Okay, so this is a reduction, tree colorability, also NP hard. And of course, tree colorability is in NP because if I give you a graph and I claim that this is tree colorable, I can give you the coloring and then you can verify in polynomial time that that's a valid coloring with three colors. So all of these problems are NP complete. And actually, I have put a link on Canvas to a list of famous NP complete problems. There are tons of them. And of course, all of them are equally hard because you can find reductions between any two of them. Some of the reductions are more human readable, but some of them are not. And even when it's not human readable, we know that the reductions exist, right? Because that's the whole point of completeness. All of these problems are in NP, and all of them are NP hard. So when a problem is NP hard, you can take any problem in NP and reduce it to it. So you can reduce any problem here to any other problem here. It's just that the reductions sometimes become really complicated. Okay. So let's say that you've been hired by some software company and they have given you a problem to solve, and you've been working on it for several days or several months or years, and you can't solve it, and they want to fire you now. And suppose that you prove that this problem is NP-hard, okay? So let's say I have a problem L, or I don't even need to give it a name. I have a problem and it is NP-hard. Okay. What does this mean? Well, this means that you don't know a polynomial time solution for it, and neither does any other computer scientist. But you cannot go to your boss and just say, hey, this problem is NP-hard. I can't do anything, right? Because actually, a lot of the real-world problems that you will face are NP-hard. So the question is, what do we do when a problem is NP-hard? Well, there are several ways to attack it. We know that we cannot find polynomial time solutions, but maybe for that particular use case, it's fine if you have an exponential time solution or a solution that takes more than polynomial time. So the next steps, and these are the steps that you will take in 5711, are to look for non-polynomial solutions, non-polytime solutions. So maybe you find a solution that takes exponential time, but it's still manageable for the real world use cases. Maybe the real world use cases are so small that you can solve them even with an exponential time. But we also have other tricks. So what does it mean when a problem is NP-complete? You see, the whole concept of NP that we defined was based on Turing machines. But if you can somehow do a kind of computation that is outside the norm of the Turing machines, if you do something that Turing machines cannot do, then the hardness doesn't really apply to you. Okay. This was the hope that a lot of people had with quantum computing, but it turned out it can't do anything that Turing machines cannot do. But here's the thing. What if I use randomization? So when I was defining a Turing machine, we didn't have any probabilistic behavior. In a deterministic Turing machine, from every state and every entry on the tape, you know exactly where you have to go and what you have to do, right? And even in the cases where there was non-determinism, there is no chance. When you have non-determinism, it's very important that you understand non-deterministic behavior is not the same as probabilistic behavior. Remember, non-determinism is magic. It's always doing the right thing that would end up accepting the input. It will not flip coins and do things randomly. So generally, in the Turing model of computation, we don't have randomness. And actually, it's a very philosophical question at this point in time, whether computers can really create randomness. But we have pseudo-randomness, and pseudo-random functions are functions that give outputs that look random to us, and hopefully they are. But basically, you can look into randomized algorithms. And what happens when you're designing a randomized algorithm? Well, you're making an assumption. You're going to assume that you have a Turing machine, but this Turing machine also has access to a source of randomness. So let's say that your Turing machine, instead of one tape, has two different tapes. And on the second tape, there is a sequence of random zeros and ones. And someone has guaranteed to you that this sequence is really random. And it was generated, like every one of them was generated independent of the other elements in the sequence. And with probability half, it's a zero. With probability half, it's a one. If you have access to this kind of randomness, can you then find a faster algorithm? And that's the whole field of randomized algorithms. And there are many cases where a problem is NP-hard, but you can use randomized algorithms to find solutions that solve the real-world cases, the real-world instances of the problem with a high probability. Okay. Now, what else can we do? Well, The other thing we sometimes do is using approximation algorithms. Okay. So this is mostly for optimization problems. So we've been talking about decision problems mainly, but let's say I have an optimization problem. I want to minimize or maximize something, and the problem is NP-hard. Maybe I can find a good enough approximation. Maybe I want to maximize my revenue, and I say that, well, that's NP-hard, but I find an algorithm that guarantees you at least half of the possible maximum amount. Okay, that's an approximation. And the thing that I'm actually going to teach you, which is none of these things, is parameterized algorithms. Okay, so for all of these, go to 5711, but this one is today. So what's the idea in parameterized algorithms? The idea is very similar to what we saw for Knapsack. Look, for Knapsack, I cannot have a polynomial time algorithm unless P equals NP. But I had an algorithm with this kind of runtime. And if you look at this runtime, again, we said that in the worst case, it's not really bounded by any polynomial. But what's interesting here is that I'm analyzing my runtime not just based on one variable, not just based on the length of the input, but based on two different variables. Okay. Now, here's the thing. In the real world instances of Knapsack that you will see, usually the capacity of your Knapsack is small. It's very unlikely that you have to solve a real world problem in which you have a Knapsack with a capacity of 2 to the power of 64 or something, right? So if you have an algorithm like this, it will very likely work for the real world use cases, even though it's not a polynomial time. So let me give you an example of this, and let's do our favorite problem, vertex cover. So remember the problem of vertex cover? The input is just a graph and some number k, and you want to decide whether you can take k of the vertices so that they cover all of the edges of the graph. Okay, so my input is a graph G and some number k. And the question is, are there k vertices that touch all of the edges? Okay. We've already seen that this is NP-complete. It's in that figure, it's here. Okay. So I cannot hope to find an algorithm that runs in polynomial time. But suppose that I'm solving some real world problem and I see that my problem is equivalent to vertex cover. I can't just give up on it. What if in my real world instances, the number k is small? So let's say I guarantee to you that k is very small. Can you then solve it in polynomial time? So here's a very simple idea. Let's say I try all the possibilities. So I have this graph. Let's say this is with n vertices and m edges. And the question is there a set of k vertices such that they cover all of the edges? Well, let's try all sets of k vertices. Okay. How many sets of k vertices can I have? Yes. So I just do brute force, and I have to try n choose k possibilities. All the subsets of size k. How much time do I spend to actually try a possibility? So if I have a subset of size k of my vertices, I'm just going to go over every single edge and check if one of its endpoints is in my set, right? So I'm going to spend OM per try. So my total runtime is going to be O n choose k times m, and n choose k is basically n to the power of k up to some constant, let's say, because I'm assuming that k is small again. So this is the runtime that I'm getting. I'm getting O n to the power of k times m. And if I want to be even sloppier than this, I can say this is O n to the power of k plus 2, because m can be at most n squared. Okay. Now, of course, this is not polynomial time. But if you only care about the instances of the algorithm where k is small, if in all the real world instances that are given to you, k is at most 2, then this is n to the power of 4. So it's polynomial time if k is a constant. Okay. In general, we can use this to define another class called XP, and we say a problem is in XP, and XP stands for piecewise polynomial. It's not the Windows. A problem is in XP if it can be solved in this kind of runtime. It's solved in O n to the power of some function of k. Okay, this is and this f can be any function, any computable function. So basically, the idea is that I don't care what the dependence on k is, because I'm only caring about the real world instances where k is small. So I know that k is, let's say, at most 5. Because I know that k is at most 5, f of k is also going to be bounded by some constant. So n to the power of f of k is going to be polynomial for all practical purposes. Okay, not in theory, but at least for all practical purposes. But this is not good. Let's say that I want to solve this vertex cover problem. And this is my runtime, n to the power of k plus 2. And let's say my k is small. Let's say I'm looking for vertex covers of size 5. So this is n to the power of 7. Now, yeah, that's polynomial. If someone guarantees to me that k is always 5, it's polynomial, but it's a bad polynomial. Right? The degree of the polynomial depends on k. And like if I have n to the power of 7, I cannot really scale this up. I can maybe solve it for n equal to 1000, but what if n is bigger than that? So I don't like this kind of dependence. I would actually much prefer it if the dependence on this second parameter k is just as a multiplicative factor. So what do I mean by that? This is what we call FPT. And FPT stands for fixed parameter tractable. So a problem is in FPT if it can be solved in this kind of runtime. And by the way, when I say it can be solved, I mean that there exists a Turing machine that solves the problem and has this runtime. Right? So if it can be solved in O n to the power of some constant times some function of k. Okay. So, and here this c does not depend on n or k. So the idea is that I'm fine if I have non-polynomial dependence on k, but I don't want this dependence to be in the power of n. I want it to just be on the side. In other words, I don't like n to the power of k plus 2, but I would be happy with something like n times 2 to the power of k. This is fine, because I know that my k is small. If my k is at most 5, then 2 to the power of k is a constant. It's 32, hopefully. And so it's just 32 times n, and it scales up linearly. If I have bigger and bigger instances, but my k is still small, I can solve them if I have this kind of runtime. So we prefer this to this. We prefer FPT to XP. Okay. Now, we've seen an XP algorithm for the vertex cover problem. Can we find an FPT algorithm? Okay. Let me show you one very weird idea. Let's say that I have my graph. So this is my graph. And let's say the question is whether I have, what is actually the optimal vertex cover here? I can do 1, 2, 3, 4, okay. Okay, let's say my question is that with this graph G, can I have a vertex cover of size 4? So this is my question, okay? Now, I just pick any edge. And I don't say I pick randomly, I'm saying I pick arbitrarily. I pick the first edge according to some order. Let's say I look at this edge, for example. Now, if I look at this edge, what can I know about a vertex cover? I know that a vertex cover has to cover one of the two endpoints of this edge. So either this vertex is in my vertex cover or this one, right? So, or maybe both of them. Now I can do a case fork. I can say, which one do you want to take in your vertex cover? So let's say that for this graph, I wanted to find a vertex cover of size 4. I take the two cases. I have to copy this. So this is one case, and this is my other case. So my first case is that I take this vertex, the left vertex, into my vertex cover. So let's say this is in my vertex cover. So what do I know? If this vertex is in my vertex cover, all of the edges that were adjacent to it are already covered by this vertex. So I can just delete all of those edges because they're already covered and I don't care about them anymore, right? And now I have to cover this remaining graph. But I have to cover this remaining graph with a vertex cover of size 3. So my K, my budget goes down. Okay, what was the other case? The other case was that I've put this one in my vertex cover. So again, it covers all of the neighboring edges, and I will have this remaining graph, and I have a budget of 3. So I started with a big graph. I did a divide and conquer, basically. I changed the problem so that if I can find the answer to either of these two problems, the answer to both of these two problems, I know the answer to my original one. So if I can find a vertex cover of size 3 here or a vertex cover of size 3 here, then I have a vertex cover of size 4 in my original instance. Now, this might look like a terrible divide and conquer, right? Because I'm starting with my graph, let's say n vertices, m edges. And I'm literally just taking one vertex and a few edges out. In the worst case, I might be taking only one edge out. So if I want to write a recurrence relation, it's something like this. Let's say I only look at the number of vertices. So let's say I want my time based on n and k. I have this. T of nk is 2t of n minus 1 k minus 1 plus some extra time. What is the extra time? The extra time is figuring out which edges I had to delete. And that's actually OM. But let's say ON squared. This is my recurrence relation here. Now, horrible recurrence relation if you don't look at K. It's like T of N is 2T of N minus 1 plus something. So it's definitely exponential. But remember, the important point here was that I said my K is small. So I can keep doing this. Instead of just writing this recurrence relation, I can say, let's continue this algorithm. So I want to solve this one. I'm going to pick an edge and say, I have to either put this side of the edge or that side of the edge into my solution. And that would reduce this problem to 2 instances of the same problem where my budget for the number of vertices that I can put in my vertex cover is now 2, right? And this goes on. Of course, I need a base case. I need to stop this recursion at some point. When would I stop my recursion? Well, if I run out of budget, if I get to a point where I'm asking, does this graph have a vertex cover of size 0? Okay. in that case, the answer is yes, if and only if the graph has no edges. Because if you have an empty graph, that has a vertex cover of size 0. Okay, so when my budget becomes 0, I know the answer. What is the other case when I know the answer? If I run out of edges, let's say I have some budget remaining, but I've already covered everything. There is no edge to cover anymore. So in that case, the answer is yes. You can cover everything. Okay, so basically now I have this recursive algorithm. And the important point is that if you analyze it just based on the input size, you will just see that this is an exponential time algorithm. It's like T of n is 2T of n minus 1 plus some extra work, right? So your runtime is 2 to the power of n times something, which is not good. But when you analyze it based on both parameters, you get something like this. Again, let me write this. So I have T of n and k, the time that I need on an instance with n vertices and parameter k looking for a vertex cover of size k, is going to be 2t of n minus 1 k minus 1 plus, let's say, m plus om. Okay. Now here's the thing. I can just look at this recursion tree. And what is the height of this recursion tree? Every time that I'm going down, my n is decreasing, but my k is also decreasing. And I said, I assume that k is much smaller, so k is going to run out first. So the height of this tree is going to be k. And every time the branching factor is 2, every node has 2 children. So I have 2 to the power of k nodes here. And at every node, I'm spending OM time because I'm removing some edges at every point of my recursion tree. So my total runtime is actually O2 to the power of k times m. So this is the runtime that I get, OM times 2 to the power of k. Okay. And again, as usual, I'm assuming that initially the number of edges is more than the number of vertices. I don't want to write n plus m. Okay, now this is much better than the previous runtime. Again, if I assume that I have a very dense graph, let's say m can be at most n squared, this is a runtime of O(n) squared times 2 to the power of k. So if I only care about the inputs where k is small, then 2 to the power of k is going to be a constant number, and I can actually handle really huge inputs because then my algorithm has a runtime of O(n) squared, right? Whereas here, because the k appeared up here, I couldn't really scale it up that well. So this one is much more scalable. And this is one of the things that we do when we see that a problem is NP-hard. I'm going to show you another solution for the same problem. And this is kind of a different solution. The idea here is, suppose I start with an instance of my problem and I want to simplify it a little bit. Okay. Can I have a way of making my graph a little bit smaller? Or can I have a way of reducing my budget k by a little bit? And I don't want to do divide and conquer because I don't want to have recursion. I don't want to have many different instances. I want to just make my graph a little bit smaller. And my hope is that I find a rule that makes the graph smaller, and I keep applying this rule until my graph becomes so small that I can just do brute force. Okay, that's my hope. So this is actually what we call kernelization. I'm just going to drop this word so that you know what to Google. Okay, so let's try this. Let's say I have a graph as my input and I have some budget k. The question is, do I have a vertex cover of size k? How can I simplify my graph? So first of all, let's say if I have a vertex of degree 0, I can get rid of that vertex, right? Because it's not going to be in any vertex cover. So this is going to be my rule 1. My first rule is that if the degree of some vertex v in the graph G is 0, Then I take the instance gk, and I say that instead solve g minus v. Okay, so just remove that vertex. Okay, not a very useful rule, but at least sometimes it simplifies my graph. Now, let's say I have a vertex of degree 1. Would I ever put a vertex of degree 1 into my vertex cover? If I have a vertex of degree 1, I have this vertex, it's connected to some other vertex. Now, this other vertex is potentially connected to some other places as well. But this one has a degree of 1. So instead of putting this in my vertex cover, it always makes sense to put this one in the vertex cover because it covers everything that the other one covered, which is basically this edge, but it potentially also covers something more. Okay. And also, because I know that I have to cover this edge, I know that I have to put one of them in. So the only optimal choice, going back to our greedy session, is to put this neighbor in if you have a vertex of degree 1. So my second rule is that if I have a vertex of degree 1, I would put its neighbor into my vertex cover. So this is rule 2. If the degree of a vertex v in G is 1, and let's say u and v are connected, then I put u into my vertex cover. So what happens here? Gk becomes g minus u minus v. So I'm removing both vertices. And my budget is also going down because I put u into my vertex cover. So if I can solve this instance, if the answer to this instance is yes, then the answer to this one is also yes. Okay. These are 2 rules for simplification. But can I simplify even more? So up until this point, we've looked at vertices that have small degree. What if I have a vertex that has a very large degree? Let's say I have a vertex that is connected to every other vertex. Don't you agree that I have to put that large degree vertex into my vertex cover? So basically the idea is this. Suppose that I have a vertex and it has a bunch of neighbors. Okay. I can choose whether to put this vertex in or not. But if I don't put this vertex in, I have to put in all of its neighbors because all of these edges have to be covered. So if this central vertex is not in my vertex cover, then all of these vertices are forced to be in my vertex cover. Okay. But I'm looking for a vertex cover of size k. So if I have a vertex that has degree k plus 1 or larger, I cannot afford to put all of its neighbors in the vertex cover. So I am forced to put that vertex in the vertex cover. So this is my third rule. Rule 3 is going to say if the degree of some vertex v in the graph G is at least k plus 1, then when you have the graph G and looking for a vertex cover of size k, you have to put this vertex in. So you should just look at the graph G minus v, and now you're looking for a vertex cover of size k. Okay. Now this is great because I have 3 different rules, and my first 2 rules get rid of vertices of low degree, and my last rule gets rid of vertices of high degree. So let's say I keep applying these rules over and over again, as many times as I can. I will end up with a graph in which every vertex has a degree between 2 and k. Okay. Now, here's the thing. I applied all of these. So after applying all the rules exhaustively, rules 1, 2, 3, as many times as possible, I know that the degree of every vertex is somewhere between 2 and k. And this is for every vertex. Okay. And by the way, my k might have changed already, right? Because sometimes when I apply the rule, my k goes down. Now, I have a graph. The degree of every vertex is at most k. And I'm asking, is there a vertex cover of size k? But if the degree of every vertex is at most k, it means that this vertex can cover at most k edges. So if I take k vertices, they can cover at most k squared edges. So at this point, if I have more than k squared edges, I know the answer is no. I know it's impossible to find a vertex cover. Because again, every vertex can cover at most k edges, and I have more than k squared edges, so I cannot cover them with k edges. So here, I just have a simple if in my code, which says if the number of edges right now is more than k squared, then just return false. I can't do it. Otherwise, I'm now in a very small graph. I'm in a graph in which the degree of every vertex is between 2 and k. And also I have at most k squared edges. So you see, I was assuming that k is a small constant. So I'm saying my graph has very few edges now. It has only k squared edges. How many vertices can it have? If I have a graph that has k squared edges and the degree of every vertex is also at least 2, okay, I let you solve that. You can have up to 2k squared vertices, right? But okay, so I want you to prove this lemma yourself because we ran out of time. The lemma is that this graph has OK squared vertices. Okay, but if I now have a very small graph, if my graph has OK squared vertices, then I can just apply this algorithm and my n is now k squared, right? So, or I can even apply the very first algorithm that I had. I can just do brute force. I can look at all of the subsets of size k of the vertices because I have only k squared vertices. Even if I brute force, my brute force runtime would be exponential, but it would be exponential in k, and I don't care about k. K is small. Okay, what is my runtime dependence on n? Well, every time that I'm applying these rules, the size of my graph is actually going down, right? So you can easily claim that the total number of times that you apply these rules is at most n plus m, right? And applying each rule also doesn't take more than, let's say, linear time. Yeah, it's easy to figure out if you can apply these rules. Some of them you can find in constant time. So overall, we started with a big graph. We did some polynomial time processing on it. And we ended up with a small graph, a graph where the size is bounded by some function of k. And then I can say, because my graph is small now, I just do brute force. And it would be polynomial time as long as k is a small constant. Okay, I'll see you in 5711, hopefully.